Chapters 3 and 4 are about derivatives and applications. That's what exam 2 for you is about. Pretty much everything you should learn about derivatives and applications in a Calculus 1 course, the heart of the course. At the beginning of chapter 3, we started with a bunch of derivative rules. The first rule really is linearity, that the derivative of a sum is the sum of the derivatives, and also the derivative of a constant times a function is that constant times the derivative of the function. Those rules can be combined into the derivative of an arbitrary linear combination. You could call it, say, C1 times f of x plus C2 times g of x. And I could even extend this to more than two functions. Any finite number of functions, we apply this rule all the time when we take derivatives of polynomials that maybe have 5 or 6 or 7 terms to them even. We say the derivative is the first constant, C1, times the derivative of the first function, plus the second constant, C2, times the derivative of the second constant, of the second function, G. That's called linearity. Another name for it is a superposition principle. It's got analogs in physics when you use the word superposition. It's very important, though we don't think about it very much. If this were not true, calculus would not be nearly so useful. It's very, 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 very good that this is true. And again, we use it all the time. We also had, well, technically in chapter 2, we had the power rule, but I'll include it here in chapter 3 as well, that the derivative of x to the n power is n times x to the n minus 1 power, and that works no matter what n is, including if n is something strange like pi or even e. You know, the derivative of x to the e power, just use a prime notation here, is not x to the e power. This is not an exponential function. This is not the same as e to the x. It's a power function. The variable is in the base. X is the variable, e is a constant. It fits this pattern with n equal to e. The answer is e times x to the e minus 1. Of course, the derivative of e to the x, that exponential function, is just e to the x. It's a different kind of function. Okay? A different kind of rule applies. Yes, n can be anything here, and that power rule applies. It can also be fractions, which also means you should be able to apply it to take derivatives of, say, x squared times the 5th root of x cubed. How? Write these two functions both as power functions. The 5th root of x cubed is the same as x to the 3/5 power. You could use the product rule here, but you don't have to because you can just add those exponents. 2, getting a common denominator of 5, is the same as 10/5. 10/5 plus 3/5 is 13/5. Or what would that be? 2.6 if you prefer, though you should feel comfortable with fractions. Bring that power down, 13/5 x. Subtract 1, 13/5 minus 5/5 is 8/5. There's the answer. There's one way to write the answer. You also could write the answer as 13/5, say, x to the 1st power times the 5th root of x to the 8th. There's various ways of writing it. Okay, that's one way of writing it. But this is good enough just to get an answer. Question?
Is decimal form acceptable?
Decimal form is okay. Yes, 13/5 could be written as 2.6, and then this would be 1.6. Yes, that is okay. Another question?
Does this hold up for imaginary numbers as well?
It does turn out to hold up for imaginary numbers. N could be the imaginary unit I or any other complex number, in fact, and it does work, though understanding what that means is less clear. Another question?
Where did you get that
There. That was a mistake. Thank you for noticing that. This should be x cubed here instead of x to the 8th. Okay, so that's the power rule. We also apply this when we are taking derivatives of polynomials. We combine linearity in the power rule when we're taking derivatives of polynomials. For example, 4x cubed minus 5x squared plus 6x plus 2. That's 4 times x cubed prime minus 5 times x squared prime plus 6 times x prime plus 2 times what? X to the 0 prime. You could think of it that way if you wanted to. You don't have to. X cubed prime is 3x squared. X squared prime is 2x. X prime is 1. And x to the 0 power prime is 0. This simplifies to 12x squared minus 10x plus 6. Of course, you got enough practice now that you can just jump from here to here, and that's fine. Get the answer quickly. It's fine to do that, but I wanted to illustrate that the rules technically do apply. We have the rule for derivatives of exponential functions. I already mentioned one of them. The derivative of e to the x is e to the x. You might say that's the most important special rule in calculus for the derivative of a special function. And fortunately, it's the easiest to remember. The derivative of e to the x is itself. The function outputs at any value of x give you the slope of the curve at that same value of x. Amazing. If you've got a general base b, like 2, for example, then you also have to multiply by ln of b. When b equals e, we do still get the right answer because ln of e is 1. Natural log of e is 1. The log base e of e is 1 because e to the first equals e. All right, so you should know these. Then we moved on to our more general rules. The product rule, quotient rule, and chain rule. Product rule says in abstract form, I'm going to write this out. Of course, you should be able to apply the product rule whenever you need to, but you also should know its abstract form and even be able to apply its abstract form. Even when you don't know formulas for f and g, but maybe function values and derivative values, like given in a table or maybe with a graph, you should still be able to apply the product rule. There's your left function f, there's your right function g, left d right plus right d left. There you go, there's the product rule. Because the plus sign there, because addition is commutative, you could switch the order of these things. Multiplication is also commutative, you could switch the order of these things. That works for the product rule. It does not work for the quotient rule because subtraction is not commutative. The derivative of f of x divided by g of x, top function, bottom, or high and low, is low d high minus high d low over the square of what's below. Common mistake is to get the numerator in the opposite order, the wrong order. Don't make that mistake. You might wonder, maybe I talked about this question a few weeks ago. If subtraction's commutative and subtraction is also addition, how does that work? Subtraction is not commutative. You know, 5 minus 2 does not equal 2 minus 5, right? 3 does not equal negative 3. But wait a minute. Isn't subtraction Can't that be defined in terms of addition? 5 minus 2 is the same as 5 plus -2. Well, 2 minus 5 is the same as 2 plus -5. It's not the same addition. That's the problem. So subtraction is not commutative. You cannot switch the order of things in the top. And then we have the chain rule for the derivative of a composition, f of g of x. Think in terms of outside and inside functions. G gets applied first when you plug a number in for x. That's the inside function. F gets applied second. That's the outside function. The chain rule says take the derivative of the outside, but then plug in the inside function. Then extra step, multiply times the derivative of the inside function. You should feel comfortable with Leibniz notation for this as well. If u equals g of x and y equals f of u, so that y also equals f of g of x, by replacing u with g of x, you can write the chain rule as dy dx equals dy du times du dx. And it's as if you're canceling the du's to get dy dx, not literally, but you could pretend. However, if you use this Leibniz notation for the chain rule, you need to realize in the end, you got to get everything in terms of x. So even though you see a dy du there, which would typically involve u, in the end, you want to replace any u's with g of x and simplify to have an answer that only depends on x. Okay, but it's kind of a nice way to remember the chain rule. That's why we teach it. Those are our general rules. In section 3.5, we went back to more specific rules. The derivative of trig functions in particular, the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x, yes, it is 1 over cos squared x, but more typically people write it as secant squared x. And the derivative of secant x is secant of x times tangent of x, which is also the same as sine of x divided by cos squared x. What about the derivative of cotangent and cosecant? Do you need to know those? They can be found, but you don't need to know them, okay? You can use the fact that cotangent is cosine divided by sine, or another way to think of it is 1 over tangent, and use the quotient rule to derive the derivative of cotangent. And cosecant of x is 1 over sine of x, and you can derive its derivative with the quotient rule as well. But even though that can be done, we don't typically bother. These are good enough for us. And it's at this point, well, let me remind you of two things. Let me remind you, in order to use these equations, it is assumed that x is measured in radians if you're thinking of it as an angle. It's assumed that you're thinking about the ordinary graphs of sine, cosine, tangent, and secant that we defined by thinking about the unit circle definition of those functions, thinking of x as being an angle measured in radians. But then we make a graph of it, then x becomes the horizontal axis, and we don't have to think of it as an angle anymore. Okay? So x has to be in radians. Your calculator needs to be in radian modes for this to make sense. Second thing I want to mention here, to bring up right now, is start relating what I've just been talking about the last few minutes to indefinite integrals as well. We have talked about indefinite integrals as an extra subject in chapter 3. It was technically from chapter 6 in the textbook, but I like to introduce it early. Indefinite integrals are easier than definite integrals. Effectively, when you write the integral sign and you write your function, in this case, I'm going to write a cosine of x and then put a dx to emphasize the variable as x. just an indefinite integral sign with no limits of integration. All this means is write down the most general antiderivative of this function. Since the derivative of sine is cosine, the most general antiderivative of cosine is sine plus c. You don't want to forget your plus c. We want to allow for arbitrary constants here because, well, any arbitrary constant still works for one thing, because the derivative of a constant is 0. It also turns out by adding constants here, it helps you solve problems. Especially I'm thinking of differential equations. If you take the class called differential equations, making sure you put the plus c there helps you. That's not the end of the problem. You got to finish it from there. You got to find what's called the initial value of the function based on some initial condition, like maybe y of 0 is 7 or something. Well, since sine of 0 is 0, in order for this to equal 7 when x is 0, c would have to be 7. You have to be able to allow yourself arbitrary constants to be able to solve those kinds of equations. So it's a good thing to get in the habit of, and I do require it. It is assumed that you will put it there when you write indefinite integral signs. For the antiderivative of sine of x, since the derivative of cosine is negative sine of x, the antiderivative of sine of x is negative cosine of x plus c. So it kind of switches around, right, from what's going on with the derivative. It has to. The derivative of sine is cosine. Therefore, the integral of cosine is sine plus c. Derivative of cosine is negative sine. So integral of sine is got to be negative cosine, because if you differentiate this, the negative sign stays there initially, but then you get an extra negative sign from this fact, and then the two negative signs cancel to give you a positive sign, which is what you see there. These facts about the derivative of tangent and secant, to tell you the truth, the thing they're most useful for is doing integrals. And that applies to some other derivatives here as well that I'll talk about in a minute. For example, the integral of secant squared x, because the derivative of tangent of x is secant squared, is tangent of x plus c. If you didn't know that the derivative of tangent of x was secant squared x, you'd have no idea what to do there. It's because you know this fact that you can say that fact very quickly. Does the integral of secant squared x come up in calculus 2? Yes, it does. In applications even. And in calculus 3, which is multivariable calculus, the integral of secant squared comes up in applications. It is relevant for applied problems. Kind of amazingly, this is an aside. You don't need to know this. Here's an aside. The integral of secant of x, while it can be done, is very complicated. And the integral of secant cubed x, while it can be done, is also very complicated. Secant squared is a special case that turns out to be easy by memorization. I happen to know the answer to this off the top of my head. It's because I've done it so many times. The answer to the integral of secant of x is natural log of the absolute value of secant of x plus tangent of x plus c. What? Log? Yes, natural log. I won't show you why. Okay? Likewise, this integral, this derivative fact leads to a fact about integrals, that the integral of secant of x times tangent of x would just be secant of x plus c. The aside comment, again, was that these are complicated. You don't need to know those for your calculus 1. Any problems in calculus 1, but they do come up in calculus 2. Integrals in general are much harder. Sometimes they are very, very complicated. Sometimes they are even impossible. Oh, here's another aside. that will be very relevant for us the last couple weeks of class. Integrals like this, say the integral of cos squared x, it's more than just complicated, it's impossible. And you can actually prove it's impossible. Well, is it really impossible? With a caveat. And the caveat is this impossibility is with respect to ordinary functions that you are used to from pre-calculus. Integral of cosine of x squared does exist. It is a function. It can be defined, but it's a function you've never heard of. Yes, there are hundreds, if not thousands, of functions that you have never heard of to this point in your life. There are hundreds, if not thousands, that I've never heard of. I've heard of more than you, but there are hundreds, if not thousands, that I have never heard of. Are they useful? Yeah. They wouldn't be out there if they weren't useful. They are specialized kinds of functions. They're called non-elementary functions because they're not the kind you see in elementary school. No, I meant to say not the kind you see in pre-calculus and calculus. You don't see these functions in elementary school. That's a joke, right?
Well, you don't.
You don't. You're right. Just as all these functions were new to you when you learned pre-calculus and trigonometry, there are other functions that are new to you that you've never heard of before. From that point, we went on in section 3.6 to derivatives of inverse functions, examples of which include the derivative of natural log of x being 1 over x. This is if x is positive because the domain of ln of x is only positive numbers. We also did show that the derivative of natural log of the absolute value of x is also 1 over x. And that's if x is not 0. It could be negative there. And that does mean that the integral of 1 over x should in general be written as natural log of the absolute value of x plus c based on this fact down here. Actually, that's not even the most general antiderivative. This is a bit of a fib. An even more general antiderivative of 1 over x is a piecewise defined function. You don't need to know this for the test, but ln of x plus, say, c1 if x is positive, and ln of negative x plus c2 if x is negative. And I could have written an absolute value of x there instead of a negative x, because if x is negative, then negative x is positive. Don't worry about that. That's another aside. More inverse functions include the derivative of inverse tangent of x, also called arctangent of x. And you should be okay with either notation, is 1 over 1 plus x squared, which does then mean the integral of 1 over 1 plus x squared is something to memorize, inverse tangent of x plus c. As with those trig function ones with tangent and secant, the main application of this fact is this fact. You want to know the derivative of inverse tangent to be this so that you can integrate that. That's more important for applications. Plenty of applications of integrals like this in calculus 2. Corresponding fact for inverse sine of x, also called arcsine of x, is 1 over the square root of 1 minus x squared. So that, yes, the corresponding fact for integrals, which is still pretty important, but maybe a little less important than the previous one, is that the integral of 1 over square root of 1 minus x squared is inverse sine of x plus c. I'm about to write down an equation you don't technically need to know for the test, but I think I mentioned it once. this is another aside, the derivative of inverse cosine of x, also called arc cosine of x, amazingly is just the opposite of the derivative of inverse sine of x, which means you also can write this integral as negative inverse cosine of x plus c. Isn't that interesting? Why would that happen? I actually encouraged you one day about 3 weeks ago to explore why, maybe 4 weeks ago, by adding these two functions, something interesting happens. And that if you do that adding and you graph the sum, it will be more clear why the derivatives are opposites of each other. Give it a try after class. I'm not going to do it now. Okay, just kind of an interesting fact, but you don't need to know it for the test. Are there any functions that I'm missing? I don't think so, though. We also did have the abstract formula for the derivative of a general inverse function that you should know and be able to apply. The derivative of f inverse of x is 1 over the derivative of f, where you plug in f inverse of x into f prime. That's a general fact. You remember deriving these facts? We did a bunch. You should be able to do those derivations on the exam. For example, to derive the derivative of ln of x, it's best to use the fact that e to the ln of x equals x if x is positive, and then differentiate both sides with the chain rule, assuming ln of x is differentiable when you do so. Remember doing that? Maybe you don't. We did it. We also did it, for example, to find the derivative of inverse tangent using this equation. That's actually true for all x. Inverse tangent of x has a domain equal to all x. Its range is not all x. It's the graph of inverse tangents looks like this. It's got two different horizontal asymptotes at negative pi over 2 and positive pi over 2. So it's defined for all x, but its range is not all possible values of y. Anyway, this is true for all x. Then you differentiate both sides, including the left side with the chain rule, assuming inverse tangent is differentiable. Do you need to be able to prove other derivatives? You should be able to do basic limits for derivatives of simple functions, say like x squared or x cubed. That was on even exam 1. I'm not saying it couldn't be on exam 2. You should be able to do that because in the beginning of chapter 3, there were various limit calculations. We did sort of derive the derivative of e to the x as well, and sine and cosine using trig identities. It was a while ago. You may want to look back in your notes for those things. Might have even been before exam 1, late September, early October, it might have been. We did these derivations. We talked about how to derive the product rule and quotient rule. Product rule, we made the picture of the rectangle. Probably wouldn't put a full proof of the product rule in the test, but you should study the proof anyway and understand it. Maybe I'd ask you to explain part of it. Maybe, I don't know. Quotient rule, we derived using the product rule and the chain rule. We derived that, and that's simple enough. You should be able to do it. Write f of x divided by g of x as f of x times g of x to the negative 1 power. Use the product rule and the chain rule to derive the quotient rule. At this point, we moved on to implicit functions and multivariable calculus and local linearization. Trying to put all those ideas in the context of multivariable calculus. Oh, take a simple example here, like x squared times y cubed. Oh, maybe I should do something a little else here. Plus x, let's say. That's an example of a multivariable calculus function. Certainly you should be able to plug numbers in to find outputs. You know, what is f of 2, -1? Replace x with 2 and y with -1 and simplify. 2 squared is 4, -1 cubed is -1, so we get -4 plus 2. The output is -2. So you should be able to plug numbers in. Should you be able to graph multivariable functions? That's probably too complicated for us. I mostly, even myself, rely on technology for that. But you should understand the idea of the graph. The concept is you've got a three-dimensional coordinate system. You imagine this to be three-dimensional space, an x-axis coming out of the paper towards you, a y-axis going to the right, and a z-axis going upward. And the concept is you let x and y vary over the entire plane, where z is 0, and you find the outputs, and you plot the corresponding points. And what you in general get is some sort of surface. In general, it could be some wacky-looking surface that could be the graph of your multivariable calculus function. Though we did special cases where one looked like kind of like a bowl shape. That was x squared plus y squared. What does the graph of this one look like? I have no idea offhand. I'm sure it does not look like that. And you should also understand the concept of level curves, where we imagine cutting this surface with horizontal planes at constant values of z, z equals c. For example, z equals -2. I drew it so c looks like it's positive here, but it could have been negative. When you slice a surface with a horizontal plane, you typically get a curve. It's called a level curve, and you can make a graph of the level curve in an ordinary xy plane. Like, what is the level curve where this function equals -2? One point I know for sure it includes is the point 2, -1. 2, -1 is one point on this curve where this equals that. All the points where this expression equals -2. What are some other points? I don't know. Could I estimate what the curve looks like near this point? I can try. I can try using implicit differentiation to try to estimate, to try to find the slope of the tangent line there to the curve, assuming it exists. Now, it might not be a differentiable curve. That's possible, though rare in these kinds of circumstances. It's also possible, though rare, that we might be at a point where the tangent line is vertical and has infinite slope. And if that is true, then implicit differentiation is going to give us a dividing by 0, and we would see that. But probably the slope does exist and is not infinite. So let's just go ahead and assume that's the case and use implicit differentiation to try to find the slope there. Take this equation. I'm going to rewrite it again. X squared y cubed plus x equals -2. And assume y is a function of x near the given point. Assume that. Is it a function of x? Actually, it's a function of x we actually could solve for. Sometimes it's complicated enough that you can't solve for it, but here we actually could solve it for it. We could subtract x from both sides and write x squared y cubed is -2 minus x. Then we could divide both sides by x squared and write this. And then we could take the cube root of both sides. And even with minus signs on the right, that's okay to do because we can take cube roots of negative numbers. That's all okay. Okay, so there's what it equals, but you don't need to know that. Instead, you can assume it and differentiate implicitly based on that assumption. And in the first term, you would need the product rule for differentiating this product, and you would also need the chain rule for differentiating y cubed. Left, d right, which I'll initially write just d dx of y cubed, plus right d left, differentiate with respect to x, Then plus the derivative of x, which is 1, equals the derivative of -2, which is a constant, so its derivative is 0. But don't stop, we're not done. With this derivative, we need the chain rule. Differentiate with respect to x, y cubed. The answer is not 0, because y depends on x. It's not 3y squared, even though we can start writing that, because we need the chain rule to multiply times the derivative of the inside function with respect to x, which is dy dx. And now you want to solve this equation for dy dx. 3x squared y squared dy dx. Bring these things to the other side, equals -2x y cubed minus 1. Now divide both sides by 3x squared y squared. And then to find the slope at the point in question, just plug numbers in. The point in question was x equals 2, y equals -1. Yeah, we're not going to divide by 0. X is 2 and y is -1. Be careful not to make a mistake. Hopefully I have not made a mistake to this point. -1 cubed is -1 times -4 is +4. On the bottom, -1 squared is +1. Looks like we get a 12. 3/12 or 1/4, if I have not made a mistake, is the slope of the tangent line to the curve at the point, which then allows us to approximate the curve near that point with a linear approximation. Tangent line approximation. How? Well, we know a point on the curve. 2 and -1. We also know the slope of the tangent is 1/4. That's the tangent line there. It's not the curve itself because it's straight. The curve itself just looks like the tangent line near this point. It's a good approximation when x is close to 2. So I can use point slope form. Y minus -1 equals the slope 1/4 times x minus 2. This is the same as y plus 1. This is the same as 1/4 x minus 1/2. Subtract 1 from both sides. Y will be 1/4 x minus 3/2. That'll be the equation of the tangent line at that point, and then its graph will approximate the curve near that point. And you should also be able to use it to approximate values on the curve near the point. For example, if x is 2.1, what is y? It's actually better to use this form of it, with 1 subtracted, say. When x is 2.1, y is approximately 1/4 times 2.1 minus 2, and then minus 1, because I'm subtracting 1 from both sides. That's 0.25 times 0.1, which is 0.025. So if I have not made a mistake, this would be -0.975. Is your approximation for the y coordinate of a point on the curve when x is 2.1. X is a little bit bigger than 2. I've moved to the right a little bit. That slope is slightly positive. Y should be a bit bigger than -1. So assuming I haven't made any mistakes, which I'm not guaranteeing. Just the idea is what I'm trying to mostly get across here. Running low on time. Oh boy. This is the further stuff, further back stuff. So, we haven't had much time for parametric equations. They just, I probably should not have done a CP, but it was good to review anyway. Hang with me here. Just a few more minutes. We need to go quicker with what remains. Let me just very quickly remind you what remains. There were there's applying linear approximations to specific functions as well, like, for example, e to the 2x or sine of 5x or cube root of 1 minus x. You could do linear approximations for all those. You did examples like that in your homework. There's also the theorems about differentiable functions, including the mean value theorem, the increasing function theorem, and the racetrack principle were the main ones we focused on. Do you need to do proofs on the test? Possibly using the constant function theorem I forgot to mention. A proof could show up on the test using that, similar to the one we did in class. After that point into chapter 4, it was mostly optimization at the beginning. That included things like the first and second derivative tests for trying to decide whether a critical point was a local min or a local max. For the first derivative test, you focused on, does the first derivative change sign, like from positive to negative at a critical point? That would mean the function itself changes from increasing to decreasing. You have a local max. If it's the opposite, changing from negative to positive, you got a local min. How do you show work for the first derivative test? Make a number line. Well, find your critical points first, make a number line, mark off the critical points, and test the sign of the derivative in the different intervals between the critical points. That's how you show your work. The second derivative test, you find the critical points, you find the second derivative, you plug the critical points into the second derivative. If you get a positive second derivative, the graph's concave up, so it's a local min. You get a negative second derivative, the graph's concave down, so you get a local max. Some critical points are neither local maxes nor local mins, like x equals 0 for x cubed. The first derivative does not change sign, even though it is 0 at x equals 0. The second derivative at 0 is 0. So it's neither a local max nor a local min. That happens sometimes, and you should be aware of that. There was the global optimization, where you had closed intervals, and you also had to check the endpoints. Not just the critical points in the interior, but also the endpoints. The global max or min could occur at the endpoints. There was the practical applied problems, the word problems. Maximizing or minimizing surface area for a given volume, for example. You can also maximize volume for a given surface area for cylinders and that kind of thing. There's the related rates, where you are assuming all the quantities depend on time and you're differentiating with respect to t, and you're relating those rates to solve for an unknown rate. Key thing is you only plug the numbers in at the very end. Then there was L'Hopital's rule for finding limits of indeterminate form, 0 over 0, infinity over infinity. There were more complicated ones. I think I'd give you just a more basic one on the test. And then there's parametric equations and curves. So we haven't had a ton of time for that. So probably if I test you on parametric equations, it would be on mostly what we talked about on Monday, which was parametrizing a line. On your homework, you also thought about circles and ellipses and that kind of thing. Bit trickier. I'll focus, if it's on your test, on lines.